Welcome to my talk on how to explain request latency with continuous profiling. My name is Richard Startin, and I work on profiling at Datadog and focus mainly on profiling the JVM. I've made various open source contributions, mostly in Java, and I write a blog. In this talk, I'll introduce continuous profiling as a diagnostic technology at the end of a funnel, which starts with latency metrics. I'm going to explain the difference between CPU profiling and Wallclock profiling, and I'll describe some types of off-CPU execution that can slow your request down. Finally, I'll describe how our Java profiling works. So I think you should start by monitoring latency so you can know if you have a latency problem in the first place. You might do this with RED metrics, where RED stands for rate, errors, durations. Along with the request rate and errors, these metrics record your latency percentiles. I see this kind of view, which many free and commercial APM packages provide out of the box as a kind of proxy for user happiness. Many users of an internet-facing service won't tolerate high latency. Let's say your P99 latency is too high, and you'll want to find the bottleneck first. You can do this by looking at traces in the percentile you care about, so let's say the top 1%. This will show you examples of your slowest requests, and if you look at enough of them, patterns should emerge. Looking at the shape of the flame chart for an outlier trace helps to identify bottlenecks. To optimize latency here, you need to move the rightmost spans to the left and shorten the widest bars. So scan downwards, looking for wide bars which don't overlap with bars to the right. This should get you to the service in a distributed system where the bottleneck occurred. The traces in the top percentile may or may not all look exactly the same, but each one shows you a pattern to investigate. Once you've found the bottleneck, you'll want to determine its cause. This is where continuous profiling comes in, which can show you execution level data for the instances where the bottleneck occurred. Profiling data is usually represented as a flame graph, which is a weighted aggregation of stack traces. This can be a very useful visualization for cost reduction, but it's suboptimal for latency analysis. To help with latency analysis, we can filter the flame graph down to endpoint level. This filters out all samples not related to the request's endpoint, but doesn't help to understand a particular request. This view is essentially an average of the execution over all requests, which includes the common ones, which are fast enough, and the 1% that are too slow and you're trying to investigate. We'll come back to this later, but I want to focus on what's actually being sampled first. When most people think of profiling, they're usually referring to CPU profiles, which help analyze on-CPU execution. But a lot of the time, request processing isn't actually CPU bound. So this is where Wallclock profiling comes in. Request processing might go off CPU for many reasons. You might be making database queries, which is something a tracer could help with. But you might spend time waiting for locks, blocked by the garbage collector, or running into lots of other runtime or OS level problems. So we need a wall time sampler to observe these additional contributors to request latency. To introduce wall time sampling, let's look at this simple program, which runs in an infinite loop. It goes on CPU in the method busySpin, and goes off CPU when it calls thread.sleep. Here's a flame graph of the program. So there are 3 main stack traces observable in this program. 2 of them end up sleeping, and only 1 of them actually uses CPU time. So if we only sample stack traces on the CPU, we lose visibility into a lot of the execution in this admittedly contrived example. So the accuracy of the CPU profile for understanding latency is determined by the ratio of CPU time to sleeping time in this example. So to help observe threads blocked off CPU, we have a Wallclock profile type, which can also be filtered down to endpoint. This shows us the stack traces we saw from the CPU profiler, that is, most of the business logic, but also the blocked request threads, which don't use much CPU, and also some locking in the request handling threads, which is also usually invisible to a CPU profiler. JVM monitor locks have an on-CPU back-off mechanism to try to avoid contention, but you'd have to be quite lucky to see this with a CPU profiler. So is this flame graph that I've just shown you, is it intuitive? There were two threads involved in the request, one for the request handler and another where the business logic runs. The widest frame was actually for the request handler, but does that mean it's the bottleneck? The request handler is actually waiting for the business logic, so that doesn't make any sense. Don't get me wrong, this visualization can still be useful, but we need something more intuitive for effective latency analysis. Introducing the thread timeline. The thread timeline lays out all of the execution data we have about a process vertically by thread group and horizontally by time. Thread groups can be expanded to see thread level execution data. To compare a timeline with a flame graph, recall the example with sleeps and busy spins in a loop from before. Here's a flame graph, including the sleeps. And here's a timeline for the same program. We have blue bars representing execution on CPU, and we have gray bars for execution off CPU when the thread is blocked. And I've also added in a garbage collection interrupting the busy spin, increasing latency. We could have seen that in the flame graph, but we wouldn't have known for sure which code was executing when the application thread was paused for garbage collection. So the timeline is a high-level view and is focused on shape and color, but we can use it to produce a focused flame graph. For instance, let's see what's going on in the common fork join pool within a time range. The flame graph shows us the stack traces involved, but the high-level view shows us when, where, and for how long there was code running in the common fork join pool, which has some diagnostic power in itself. Rendering timelines for individual requests will help us to understand outlier latency. So we want to scope profiling data to trace level. So far, we've only seen profiling data represented as an aggregate over all requests. It mixes up the typical and outlier requests. Even though we can see the sequencing and concurrency of execution with a timeline, unless we can filter down to an individual request, we'll struggle to make sense of the latency. Once we do filter the timeline down to the request level, something magic happens. We can see the critical path laid out for us, which helps focus optimization efforts. Because just speeding stuff up doesn't necessarily improve latency in a multi-threaded program. We can see the timeline for a request here. At the top, we see runtime activity and notice a lot of concurrent garbage collection. Below that, there is a handler thread, which submits tasks to worker threads and waits for completion, and does some more processing before it finally responds. To reduce latency, we need to move the rightmost blue bar to the left. A CPU flame graph would make us focus on foo on worker 1, whereas a Wallclock flame graph would make us focus on the handler itself. But instead, we need to focus on Baz on worker 3, outlined in red, because even if we make foo twice as fast, the handler will still need to wait for bar, which itself needs to wait for Baz. Baz is longer than the bar blocks combined, so this is where we need to focus. The GC is actually a distraction here because it's concurrent, so it isn't blocking the application threads. If we optimize Baz, foo would become the bottleneck, and at that point, optimizing it would reduce latency. If we do that, the subsystem of bar and Baz working together become the bottleneck, and it's no longer worthwhile speeding foo up if we're focused on latency. We might look to move the execution of Baz onto worker 2, for example, because we have two jobs doing two threads doing the job of one here. But what if that GC weren't concurrent and it was actually a stop the world event and it was interrupting the initial execution of the handler? Then we wouldn't have looked at the application threads at all because they're being delayed by the garbage collector. And we would either increase the size of the heap or reduce the allocation rate instead. And the timeline shows us what the most critical point to focus on is here. So back in the way we back into the user interface, we can see what this actually looks like with a trace at the top of the view and the timeline below. We can see something interesting happening during work expected to run on CPU. We see ZGC allocation stalls. and they dominate the CPU time. Zooming into thread level, we can see the application thread stall when trying to allocate memory. So what are ZGC allocation stalls? They're actually just something that ZGC does, and it makes the application resilient to OOM errors. ZGC is a very low pause GC, but it can't help you if your heap isn't big enough for your working set. Latency might not be the focus in a batch job, for example, and avoiding OOM would significantly enhance operational experience. You need to know what you're optimizing for, latency cost, or maybe resilience. But if you do care about latency, allocation stalls are a dead giveaway that your heap is undersized for your working set. Earlier, I said the concurrent GC running during a request was a distraction, and we focused on BAS on the critical path. But what if the code running on the application threads is running slower because you don't have enough CPU available for the GC to run concurrently with the application threads? This would force the OS thread scheduler to share the CPU between the GC and the application threads, swapping the GC and application threads on and off the CPU in time slices. We don't have a great way to show this happening yet, though the CPU utilization metric would be at or close to 100 if this is happening, but it's something to keep in mind when analyzing timelines. So there's a blog post linked here where I go into more details about a latency investigation where resizing the heap and increasing the number of available CPUs led to a drastic reduction in latency. This analysis was driven by observing allocation stalls and sparse CPU samples across a large number of threads. Scaling up might have been your first action anyway, but profiling lets you know for sure. So how does all of this work? So Datadog's Java profiler is quite opportunistic. It's integrated with a tracer. So we ship profiling in a Java agent along with our tracer. And we make use of any source of data that we can get our hands on, really. This includes JFR, which is built into OpenJDK, and records a lot of events about JVM internals. The original focus of JFR was to allow JVM vendors to diagnose customer performance and reliability problems with JVMs. And some of the data can be difficult to make sense of as an application developer, but we still make a lot of use of the events it records. We forked Async Profiler, which is an open source profiler written by Andrew Pangan, and we make use of its excellent CPU profiler. We made a lot of customizations to it and really tailored it to our needs, which was possible because of the Apache 2.0 license. And we've added several features as well, often using JVM TI, which is the JVM tools interface. We use bytecode instrumentation sparingly in places where it won't interfere with the application much. For example, in places where the tracer already applies mandatory instrumentation or in parts of the program we know are slow anyway. For example, we record latency outliers for queue time in thread pools and have a bytecode instrumentation-based exception profiler. All the data is recorded into buffers as JFR events. And every 60 seconds, we send a snapshot of a JFR recording to our backend, where we further correlate the data we collect to make it usable. Making the profiler and tracer work together is really important for request level analysis because this is how we can scope timelines to requests. The tracer provides context by updating a data structure of context indexed by thread ID, and we do this without using JNI on the hot path. Our CPU profiler capability came from Async Profiler without much modification, except to contextualize the CPU samples. It uses services provided by Linux to generate interrupts when CPU time is used. We use the timer create syscall by default to create per thread timers to schedule samples. Inside the signal handler, the JVM function async get call trace is used to get a stack trace, and the sample is recorded as a JFR event. To see how the collaboration between the tracer and the profiler works, let's look at the context data structure, which is indexed by thread ID. It starts off clear. When span X activates on thread T0, we saw span ID X in the slot for T0. Before the profiler even sees span X, span Y is activated and slot T0 is updated. Updates by the tracer can happen much faster than queries by the sampler. So updates really need to be efficient. We don't perform any JNI calls here and only need to update a byte buffer to do this. An update takes less than 10 nanoseconds. Finally, thread T0 uses 10 milliseconds of CPU time, so we take a sample. We record span ID Y with that sample. Later, the garbage collector, which runs on thread T2, uses enough CPU to get sampled, and we record a sample without any context because we can't propagate request context into runtime threads. So what about overhead? It's really simple for CPU profiling. It's very easy to reason about. So the worst case overhead is actually determined by the sampling interval. So if we use 100 microseconds of CPU time every time 10 milliseconds of CPU time is used, then that's a 1% overhead. And so if so a profiled service needs to actually use a CPU to get sampled by a CPU profiler. So if you don't use any CPU, the overhead is 0. But Wallclock profiling is very different. So the Datadog Wallclock profiler is very different to the one in Async Profiler. Wallclock profilers have very different overhead to CPU profilers because overhead scales with the number of threads. Without being careful, we could produce millions of Wallclock samples, which would produce hundreds of megabytes of JFR events per minute and would thoroughly disrupt the profile program. So we need overhead proportional to the number of active request threads until hitting a ceiling. This means that we have a sample budget and we just can't sample every thread. So sampling one thread means not sampling another. So we need to make the most useful samples we can take, which means making difficult decisions. We decided not to sample background threads. We don't need Wallclock samples of the garbage collector or JIT compiler because they impact all requests, and we have built-in JFR events for these anyway. So another class of threads we decided to avoid were idle threads, typically in oversized thread pools. It's generally not that useful to know that a thread pool, that a thread is parked waiting for work in a thread pool, unless you're looking at thread pool sizing. Avoiding sampling threads like these allows us to focus on request processing instead, which we think is more useful to users. This is obviously a bias, but the difference between bias and relevance is subjective. The flame graph shows the request activity with none of the idle threads here. And if every thread were eligible for sampling, then the timelines would be sparse, but by biasing towards request threads, we can make them very dense and descriptive. So all of this is kind of powered by an innovative sampling strategy. So to achieve this bias towards request processing, we lean on the tracer again. Whenever an untraced thread becomes traced or a traced thread becomes untraced, the tracer notifies the profiler. The profiler records the thread IDs of traced threads in a bit set and performs reservoir sampling over this bit set in the sampler loop. The threads in the reservoir are then interrupted and sampled. To visualize this, the threads bit set to the right starts off empty and the context storage clear. SpanX activates on T0 and both the context and threads bit set are updated. Context updates don't require JNI, but the less frequent bit set updates do. Another span activates on thread T4 and the bit set is updated again. A Wallclock sample is taken later. T0 and T4 are eligible for sampling and both get sampled because 2 is below the maximum number of threads we'll sample per epoch. The context is recorded on the samples. When SpanX finishes, the thread isn't associated with a trace anymore, so T0 is removed from the bit set. Next, sample T4 is still in the bit set, so it gets sampled. So let's wrap up. So continuous profiling sits at the end of a diagnostic funnel, which starts with latency metrics, how you know you have a problem at all, via tracing, how you know where the problem is, and continuous profiling should point you to the root cause if you get this far. You don't have to use it. It's okay not to get to the bottom of the funnel if you can solve your problem earlier on. So to be useful for latency analysis, timelines are generally more useful than flame graphs, and we need to take off CPU execution into account. Timelines scope to request level, visualize sequencing and concurrency to understand the critical path, and can help find the execution level bottleneck. The ability to contextualize profile samples with timestamp, thread, and trace information allow for detailed explanation of request latency. Thank you for your attention.